All right, welcome back everyone. In this video we're gonna continue our discussion on the operators, on the mathematics that's gonna help us understand transport phenomena. The focus of this video is gonna be the Laplacian. We're gonna find out what does the Laplacian measure. My goal of this video is to give you guys is to introduce you guys to the computation of how to perform the Laplacian, and also to show you what does it mean visually. All right, and this video is gonna be an attempt at giving you an intuition behind the Laplacian. Okay, we've already discussed about gradient. The gradient spits out, the output from a gradient is gonna be a vector. Okay, and that vector measures and points in the direction of the steepest change on a surface plot. Now remember that this surface plot could be a temperature profile in 3D. This surface plot could be a concentration profile of a certain species, let's say species A. Okay, surface plots. And then we talked about divergence. And the divergence, the output from a divergence is actually a scalar. And that scalar, it can be a positive or negative. And it measures the net out, okay, net outwards flow of a vector field. So, so a vector field like this is gonna have a positive divergence. Del dot of this vector field is gonna be greater than 0. Okay, just to recap. And the gradient of a vector field that looks something like this is gonna be the divergence of this vector field is gonna be negative. Okay, so net outwards, the divergence measures the net outwards. Now, okay, the star of this video, Laplacian. What does Laplacian measure? That's gonna be the goal. By the end of this video, we're gonna answer that, hopefully. Let's talk about the computation that goes into computing the Laplacian. So let's say I wanna compute the Laplacian of a temperature profile. Okay, and that temperature profile is a function of x, y, and z in Cartesian coordinates. So the Laplacian is basically del squared is basically del dotted with del applied to the temperature. So basically you're taking the divergence, as you can see here. This is the divergence. You're taking the divergence of a gradient. You're taking the divergence of a gradient. That is the definition of a Laplacian. Okay, and let's see. So this dot product right here, now we're gonna take advantage of that. The del operator in Cartesian coordinates is gonna have these partial derivative terms, partial with respect to x, y, and z. Excuse me. And dot that with the gradient. And we've seen in the previous video that the gradient of t is gonna be dou t dou x, dou t dou y, dou t dou z. Okay, and now we're gonna compute the dot product of these two vectors. Okay, the vector of the operator and the gradient. Okay, and if I can write it here, this is just gonna come out to be the second derivative, the second partial with respect to x, plus the second partial of t with respect to y, plus the second partial with respect to z. And now, okay, so now this basically right here is how I'm gonna compute the Laplacian in Cartesian coordinates. So I have my Laplacian in Cartesian. But what do each of these terms mean? What does this mean? What does this term mean, and what does that term mean? So if you go back to Calc 1, each of these terms are telling you concavity. Okay, they're talking about the second derivatives, talk about the concavity. So this is concavity in x. So concavity in y, and concavity in z. So basically you have your cavity in z. So basically you have your temperature profiles, your temperature plots in 3D, and you're gonna measure the concavities at certain points, okay? And obviously they're gonna be in 3D, which means that you're gonna need the concavity in each plane. So let's talk about concavity for a second. We're gonna go back to Calc 1. Our discussion is going back to Calc 1, and that is single variable calc for most of you guys. Okay, in graph I have graph 1 and graph 2. In graph 1, my second derivative with respect to x, as you can see, is positive, so I have a concave upwards. Now if I want to make it, if I draw two more curves, okay, I'm drawing two more curves. Each of these curves so each of these curves has a as I go from the white to the pink to the blue, the concavity is increasing. So let me just label those real quick: A, B, and C. Okay, and if I were to list these in ascending order, the concavity of A is going to be the greatest, followed by the concavity of B, followed by, and the concavity of C is going to be the smallest. And I've color coded these, and hopefully these help. Okay, so let me just make this is for graph A, graph B, and graph C. All right, now moving on to graph 2. Here I have the situation that I have here is we have a negative concavity. We have a concave downwards. Okay, so all right, this is and it's everything is, if as you move along this curve, you're being pushed down. Okay, as you move along this curve, you're being brought downwards. Okay, so that's why, hence the negative concavity. That's where the intuition comes from. Okay, so let me just tidy this up. Oops, that's okay. We can just draw it again. My world is crumbling around me. Okay, so all right, now let's make a now this second graph that I drew, and let's say this third graph, the magnitude of concavities, we can say that graph hold on, so I have graph A, graph B, and graph C, and I'm gonna leave that as an exercise to you guys, which one has the most negative concavity and which one has the least negative concavity. You can participate in the discussion, leave your answer in the comments, and hopefully we'll have a discussion about it. Okay, so that was my attempt at giving you a visual feel of the concavity, how the second derivative, what does the second derivative visualize, how you can visualize the second derivatives. And hopefully this segment gave you a good understanding of how to compute the Laplacian. And yeah, now how are we gonna update our discussion? What I'm just gonna put here is the Laplacian measures the concavity. It measures the concavity of a surface plot. All right, and I hope this video was helpful, and if you guys found anything, and if you guys feel like I've made a mistake somewhere, then please let me know in the comments. All right, thank you so much for watching.